Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, when you're looking at the latest data coming out of observational cosmology, it's really easy to get lulled into a false sense of security.
Oh, absolutely.
Yeah.
It all looks so neat and tidy on paper.
But, I mean, we talk about the acceleration of the universe's expansion driven by dark energy as if it's this perfectly mapped landscape.
Yeah.
And you've probably followed the major breakthroughs, like the universe is expanding and the rate of that expansion is accelerating.
That's the established baseline, yeah.
Exactly. But what often gets buried in the headlines is just how precarious the foundation of those measurements actually is.
Precarious is definitely the right word for it.
Because we are trying to pin down the exact equation of state for dark energy. But our primary cosmic measuring takes, which are these exploding white dwarf stars, well, they are not nearly as uniform or straightforward as we'd like to believe.
No, they really aren't. And honestly, the error bars are where the real war is being fought in modern astrophysics right now.
Yeah.
Because for the last 20 years, we've been relying on a relatively piecemeal approach to calibrating these distances.
Step-by-step kind of stuff.
Right. And it's a fascinating, deeply complex problem. The precision required to understand whether dark energy is, a cosmological constant or something dynamic that evolves over time.
That demands a lot.
It demands a level of observational perfection that the universe simply doesn't want to give us spontaneously. We have to extract it.
And that extraction process is undergoing a massive seismic shift right now, isn't it?
It really is a total paradigm shift.
Okay, let's unpack this. Because a research team from the Institute of Cosmos Sciences of the University of Barcelona recently published a framework in Nature Astronomy called CIGaRS.
Yes, CIGaRS.
And it completely throws out that traditional step-by-step methodology of measuring cosmic distances, right?
It throws it right out the window.
So instead, it fuses astrophysics, Bayesian hierarchical modeling, and this highly advanced artificial intelligence to infer the reality of the cosmos in one massive, synchronized sweep.
Which is incredibly ambitious.
It is. So our mission here is to figure out exactly how this CIGaRS framework operates, why the old methods are breaking down at high precision, and how training an AI on millions of simulated fake universes might actually be the only way we can accurately measure the real one.
It's a wild concept. But to really appreciate the sheer scale of the CIGaRS framework, you have to look at the mechanical limitations of the traditional standard candle.
The supernovae.
Right. The concept of using a type Ia supernova to measure distance relies on a specific astrophysical threshold.
Walk me through that.
So we're looking at a carbon-oxygen white dwarf that's locked in a binary system. It's continuously accreting or stealing mass from its companion star.
Just slowly siphoning it off.
Exactly. And the standard model holds that as this white dwarf steals matter, it approaches what we call the Chandrasekhar limit.
Which is about 1.4 solar masses, right?
Roughly 1.4, yes. And at that critical density, electron degeneracy pressure can no longer support the star against its own gravity.
So it collapses.
The core temperature spikes dramatically, and carbon ignites.
And it doesn't just burn, right? Like, it triggers a runaway thermonuclear detonation that completely obliterates the entire star.
Nothing is left behind. And because this detonation is governed by that strict mass limit, the resulting explosion yields a very consistent peak luminosity.
Meaning we know its intrinsic brightness. We know exactly how much light it's putting out at the source.
That's the theory, yes. So if we see that explosion in a distant galaxy, we measure its apparent brightness from Earth, apply the inverse square law of light, and we calculate exactly how far away it is.
So it's basically like knowing the exact wattage of a distant street lamp. I mean, if you know it's a 100-watt bulb, the dimmer it appears, the further down the road it has to be.
That's the classic analogy, yeah.
But the premise of CIGaRS is that this 100-watt bulb analogy is inherently flawed because space isn't an empty vacuum and the bulbs aren't all exactly 100 watts. Is it really that perfect? Space isn't an empty street.
You hit the nail on the head. The street lamp analogy is useful for a broad conceptual understanding. But when you are trying to measure the expansion history of the universe down to a fraction of a percent, the analogy shatters.
Because of all the noise.
Because the universe's street is absolutely choked with variables. First off, the bulbs themselves have slight intrinsic variations based on their environments.
The galaxy they live in.
Right. The data over the last decade has clearly shown a correlation between the absolute magnitude of a type Ia supernova and the properties of the host galaxy it resides in.
Okay, so a supernova in one galaxy looks different than a supernova in another.
Yes. Supernovae exploding in massive passive galaxies with much older stellar populations behave slightly differently than those in low-mass, highly star-forming galaxies.
Let's drill down into why that happens mechanically. Because if the physical trigger is always that exact same Chandrasekhar limit, why would the age of the surrounding galaxy alter the explosion? Does the chemical makeup of the white dwarf change?
It does, actually. The ignition process is incredibly sensitive to the progenitor star's initial conditions. An older stellar population typically has a different metallicity.
Meaning a different ratio of heavier elements.
Exactly.
Yeah.
Elements heavier than helium. And that affects the carbon-to-oxygen ratio right inside the white dwarf's core.
Oh, wow.
Furthermore, the rate at which the white dwarf accretes matter from its companion might differ based on the type of companion star, which in turn depends on the star formation history of that specific galaxy.
So a slower accretion rate changes things.
A slower accretion rate can lead to a lower central density at the exact time of ignition. And these minute shifts in the pre-explosion physics alter the amount of radioactive nickel-56 that's synthesized in the blast.
And the nickel-56 is important because...
And radioactive decay of nickel-56 is what actually powers the supernova's glow.
Ah.
So any variation there directly changes your standard candle's true wattage.
Wow. So right out of the gate, the intrinsic brightness is compromised by the local galactic neighborhood. But it gets worse when the light actually leaves the galaxy, right? Because it has to travel through interstellar dust. And this isn't just dimming the light like a fog bank. It's physically warping the wavelength profile we receive on Earth.
Dust is, without a doubt, the most notorious nuisance parameter in astronomy.
I can imagine.
When the photons from the supernova pass through the host galaxy's interstellar medium, they encounter all these silicate and carbonaceous dust grains.
And they block the light.
They scatter it. And these grains scatter shorter wavelengths, which is blue light, much more efficiently than longer wavelengths, which is red light.
So the blue light gets bounced away.
Right. So the supernova not only appears dimmer than it actually is, but it also appears artificially redder.
Okay.
In cosmology, we use the parameter R sub V to describe this total to selective extinction. The problem is that the properties of the dust, like the size of the grains, the chemical composition, it varies from galaxy to galaxy.
So the filter changes depending on where you look.
Exactly.
But if the dust properties are varying wildly and the intrinsic brightness of the white dwarf is shifting based on the galaxy's age, how have we historically dealt with this?
It hasn't been easy.
Because we have been mapping dark energy for a couple of decades now. If the foundation is this messy, what kind of mathematical duct tape have astronomers been using to hold this standard candle model together?
Mathematical duct tape is a great way to put it. The historical approach has been highly empirical and very step-by-step.
How so?
Well, astronomers use models like SOL-T2, which essentially fits a light curve template to the observational data. They derive an apparent peak magnitude, a color parameter to try and account for both dust reddening and intrinsic color variation, and a stretch parameter.
What's a stretch parameter?
Brighter supernovae actually take slightly longer to fade. The light curve stretches out over time, so they measure that. Then, after getting all those individual pieces, they apply global linear corrections.
Global corrections, like applying an average to everything.
Basically. They might look at the data and say, okay, we notice supernovae in galaxies more massive than 10 billion solar masses are about 0.07 magnitudes brighter after standard corrections. So let's just subtract that amount across the board.
Wait, that feels like trying to fix a complex optical aberration in a camera lens by just slapping a generic software filter on the final photo.
That's a very accurate comparison.
Like you see the image is too red and slightly blurry, so you globally adjust the tint and crank up the sharpness on your phone. It might make the picture look passable at a quick glance, but you haven't actually modeled the physical curvature of the glass that caused the distortion in the first place. You are just treating the symptoms, not the underlying physics.
That framing captures the limitation perfectly. When you apply those linear step-by-step corrections, you completely ignore the covariance between these physical properties.
The covariance, meaning how they affect each other.
Yes. The dust reddening, the intrinsic color, the galaxy's metallicity, and the supernova's brightness are not independent variables. They are a deeply intertwined physical system.
They all pull on each other.
Right. So when you correct them sequentially, one by one, you accumulate systematic errors. Now, for early dark energy measurements, these errors were acceptable because the statistical errors, just the sheer lack of enough supernovae, were much larger.
So the math errors were hidden by the lack of data.
Exactly. But today, we have massive data sets.
Yeah.
The statistical error is shrinking, meaning these systematic modeled errors are now the dominant barrier preventing us from really understanding dark energy.
Which is exactly where this new CIGaRS framework steps in. If the step-by-step software filter approach is failing us, we need to rebuild the entire pipeline from the ground up.
Yes, a total teardown.
And the University of Barcelona team did this by employing Bayesian hierarchical modeling, or BHM. Let's spend some time on this, because BHM isn't just a different equation, it's a fundamentally different philosophy for interpreting the universe, isn't it?
It is a profound shift in statistical methodology. You see, in a traditional frequentist approach, you look at an observation and try to find a single, definitive, true value for a parameter.
Like, the answer is exactly X.
Right, but Bayesian inference deals in probabilities and prior knowledge. A Bayesian hierarchical model constructs this multi-layered, probabilistic representation of reality.
Okay, how many layers are we talking about?
Well, at the very top of the hierarchy, you have your population-level hyperparameters. These are things like the underlying cosmological parameters that govern the expansion of the universe and the universal properties of dust distributions.
The big overarching rules. And then beneath those universal rules, the hierarchy cascades down to the individual events.
Precisely. The model descends to the latent, true physical state of each specific host galaxy. So its exact mass, its specific star formation history. From there, it maps to the latent physical state of the individual supernova inside it.
Meaning its intrinsic luminosity, its specific stretch and color.
Yes. And finally, at the very bottom layer, it maps to the actual noisy photometric data that physically hits the sensors on our telescopes.
So it models the whole journey.
Exactly. And the genius of CIGaRS is that it evaluates this entire causal chain simultaneously. It doesn't fit the galaxy, and then fit the supernova, and then calculate the cosmology.
It does it all at once.
It explores the joint probability distribution of all these variables at the exact same time. If we connect this to the bigger picture, it means linking all these elements physically and statistically to create a self-consistent reality.
I love that phrase, self-consistent reality. Raul Jimenez, a researcher at ICIGaRS and ICCUB who co-authored the study, described this as an ab initio simulation, meaning from the beginning or from first principles.
Right.
So by forward modeling the universe inside a computer using Bayesian inference, you can vary all possible parameters simultaneously to predict the exact universe we actually live in.
That's the goal.
But what struck me most was his point about unknown unknowns. The CIGaRS framework supposedly allows us to understand the effect of unmodeled systematics. Now I have to push back on that logically.
Let's go ahead.
How can a mathematical model account for a bias or a physical force that the human programmers haven't even discovered yet?
I know, it sounds totally paradoxical, but it relies on the nature of forward modeling itself.
Okay, walk me through that.
Let's say there is a completely unmodeled physical effect out there. Perhaps some strange interaction between dark matter and the supernova ejecta that slightly suppresses luminosity in a highly specific way.
Something we've completely missed in our physics textbooks.
Right. Now, in a traditional empirical step-by-step fit, that anomaly just gets absorbed into your error margins, or it subtly biases your final measurement of dark energy, and you never realize it because you basically force the data to fit your linear corrections.
You essentially sweep the anomaly under the rug because your model isn't designed to recognize the dirt.
That is exactly the issue. But in a generative forward modeling framework like CIGaRS, the causal physical links are strictly defined from the top down. So if you inject a simulated unknown, a synthetic systematic error, into your mock data, you can track exactly how that specific type of anomaly breaks the model's predictive power.
Oh, I see.
You can see the unique statistical signature it leaves behind when the Bayesian model fails to find a self-consistent state.
Because it can't reconcile the weird data with the strict laws of physics you gave it.
Exactly. So by studying how the model reacts to deliberate artificial anomalies during the simulation phase, you can look at the real-world observational data and identify if those same statistical signatures of failure are present.
Wow.
It gives you a rigorous way to bound your uncertainties and say, okay, our model is fully consistent here, but there is a 2% variance over here that points to unmodeled physics.
That is incredibly elegant. It essentially builds an immune system into the cosmology pipeline. It can actually detect when a foreign, unknown variable is infecting the data.
An immune system is a great analogy.
But, and this is a big but, the moment you start talking about jointly modeling the expansion of the universe, the star formation history of thousands of individual galaxies, the thermodynamics of their dust, and the thermonuclear physics of thousands of supernovae simultaneously,
You hit a wall.
you hit a massive computational wall, right? I mean, how do you even process that?
A massively terrifying wall, computationally speaking, because the traditional way to solve a complex Bayesian hierarchical model is through Markov chain Monte Carlo methods, or MCMC.
Okay, and how does MCMC work?
MCMC algorithms wander through the parameter space, evaluating the likelihood of the model at every single step. They basically take random walks to find the most probable answers. And when you are modeling a few parameters for a few dozen supernovae, MCMC is fantastic.
But CIGaRS isn't doing a few parameters, it's modeling the entire causal chain for tens of thousands of objects.
Right.
So if you try to run an MCMC on a hierarchical model with thousands of supernovae and full multi-band galaxy data, you're looking at what, millions, maybe billions of parameters to sample?
Easily. The likelihood evaluations become computationally intractable. It would take modern supercomputers literally years to properly converge on a posterior distribution for a data set of that size.
Years, just for one data set.
Yes. The computational cost scales exponentially with the complexity of the hierarchy. And if the theory is computationally intractable, it is functionally useless for the next generation of cosmology.
Which brings us to the technological leap that actually makes CIGaRS possible in the real world. Artificial intelligence.
Yes, the AI engine.
Specifically, a branch of machine learning called simulation-based inference, or SBI. And to be clear, this isn't a chatbot or a large language model guessing the next word. We're talking about using AI to bypass that MCMC bottleneck entirely.
Completely bypass it. Simulation-based inference, sometimes referred to as amortized neural posterior estimation, is fundamentally changing the landscape of high-energy physics and cosmology right now.
So how does it solve the supercomputer problem?
The strategy shifts the computational burden from the analysis phase to the training phase. The first step involves running the forward model, the ab initio physics simulation we just discussed.
Okay.
The researchers generate millions of synthetic data sets. They simulate millions of fake universes, drawing different combinations of cosmological parameters, galaxy histories, and dust properties.
So they aren't just feeding data into an algorithm, they are essentially teaching an AI the laws of physics by showing it thousands or millions of fake universes.
Exactly. They build a vast library of digital universes where they know the absolute truth of every single variable because they programmed it themselves. They know the exact amount of dark energy, they know the exact dust content of, say, galaxy #405, and they simulate exactly what the light from a supernova in that galaxy would look like hitting a telescope on Earth.
And then they test the AI on it.
Right. Then they introduce the neural network. Often these are specialized architectures like normalizing flows, which are designed to learn highly complex probability distributions. They feed the neural network the mock observational data, and they train it to learn the inverse mapping. The AI learns how to look at the simulated telescope data and perfectly infer the underlying physical parameters that generated it.
But wait, if we're trusting an AI that learned from a simulation, how do we know the simulation isn't just baking our own human biases back into the math?
That's a valid concern.
I mean, we've all seen AI models hallucinate or latch on to weird, spurious correlations in their training data. If the AI is just learning a shortcut based on a tiny flaw in the simulator, couldn't it confidently give us the completely wrong answer for the real universe?
That is the most critical question in the field of simulation-based inference right now. And the validation techniques they use are incredibly rigorous.
How so?
Because the AI is learning a mapping bounded by strict physical conservation laws, not just generating free-form text or images. We can test its calibration using coverage tests.
What's a coverage test?
You simulate a massive validation data set that the AI has never seen before. You run the AI inference on it and check if its 95% confidence intervals actually contain the true physical parameters 95% of the time.
So you grade its homework.
Exactly. And if the simulator has a slight bias, the Bayesian framework of SBI inherently inflates the posterior uncertainty. It essentially learns to be less confident when the data is tricky. Furthermore, the researchers perform extensive out-of-distribution testing to ensure the AI doesn't hallucinate when presented with data that looks slightly different from the training set.
And assuming that calibration holds up, the speed advantage has to be staggering.
Oh, it's night and day.
Because once that normalizing flow is fully trained, once it has paid that upfront computational cost, you can just hand it real observational data from a telescope, right?
Yes.
And it infers the entire multi-dimensional posterior distribution of the universe almost instantaneously. You basically replace centuries of MCMC supercomputer time with a single forward pass through a neural network that takes, what, a few seconds?
Seconds or minutes, yes. It's truly revolutionary. And that speed, combined with the comprehensive physics model, unlocks what is arguably the most significant practical breakthrough of the entire CIGaRS framework, the redshift revolution.
The redshift revolution.
Yes, because this AI engine isn't just processing standard data faster. It is capable of extracting high-precision cosmological constraints from a vastly simpler, far messier type of data.
Right. And to really grasp the gravity of this, we need to look at how we measure the distance to these galaxies in the first place, which relies on redshift.
Exactly.
Because as the universe expands, it stretches the fabric of space, which physically stretches the wavelength of the light traveling through it.
Right.
The longer the light travels, the more it shifts toward the red end of the spectrum. But measuring that redshift accurately is incredibly difficult. Historically, precision cosmology has absolutely demanded spectroscopy.
Yes, and spectroscopy is highly detailed but incredibly costly. It involves taking the incoming light from a single object and passing it through a spectrograph.
Which is essentially a highly advanced prism or a diffraction grating, right?
Exactly. It disperses the light into a long, continuous spectrum. This allows us to see the specific narrow absorption lines created by chemical elements like silicon or ionized calcium in the supernova's ejecta.
And those act like barcodes.
Exactly like barcodes. By measuring exactly how far those distinct chemical lines have shifted from their known rest frame wavelengths, we can calculate the redshift with exquisite precision.
But the problem with spectroscopy is the operational cost. To get a high signal-to-noise ratio spectrum, especially for a supernova billions of light years away, you have to precisely align a massive telescope, maybe using a specialized slit mask or optical fibers, and integrate the light for hours.
It takes a very long time.
You are dedicating a massive amount of incredibly expensive observatory time to a single object.
It is an absolute bottleneck for the field. It limits our samples to a few thousand objects over the course of decades. Now, the alternative to spectroscopy is photometry.
Okay, and how is that different?
Instead of dispersing the light into a detailed chemical spectrum, a photometric survey just takes wide-field digital images of the sky through a few broadband-colored filters.
So, for example, capturing all the photons through a specific blue filter, then a green filter, a red filter, and an infrared filter.
Right. And it's incredibly fast. A single exposure can capture millions of objects simultaneously.
But the trade-off is a severe loss of resolution, I assume.
A massive loss.
Yeah.
When you try to calculate a photometric redshift, which we call a photo Z, you are relying on the total flux of light captured in those broad color buckets. You don't have the distinct chemical absorption lines to guide you.
So it's much harder to read.
It creates severe degeneracies.
Let me throw out an analogy here. Let's say spectroscopy is like having the full, unabridged text of a novel.
Okay, I like this.
You can read every line of dialogue, you know exactly how the plot resolves, but it takes you a solid month to read it. Photometry, on the other hand, is like looking at the book's cover art through 4 different colored panes of glass. You can do it in 2 seconds. You can clearly see it's a sci-fi book because there's a blurry spaceship on the front. But trying to deduce the exact nuance of the protagonist's character arc from just that cover art is going to involve a lot of guesswork.
That is a brilliant analogy. And the guesswork in cosmology takes the form of physical degeneracies. In photometric data, a supernova that is at a high redshift, meaning its light, has been stretched heavily toward the red by cosmic expansion.
Right.
It looks incredibly similar to a supernova that is at a lower redshift, but happens to be heavily enshrouded in red interstellar dust.
Because they both just look red.
Exactly.
Yeah.
The broadband filters alone struggle to distinguish between cosmological reddening from the universe expanding and localized dust reddening from the host galaxy.
And if you get that wrong, your distance measurement is completely ruined. You think the supernova is much further away than it is, and your entire map of dark energy collapses.
And it falls apart entirely.
This is where older analytical frameworks failed, because they couldn't untangle those overlapping physical effects from blurry photometric data.
And this is the exact problem CIGaRS solves. What's fascinating here is that because the Bayesian hierarchical model evaluates the supernova and its host galaxy simultaneously, it breaks the degeneracy.
How does it do that?
The AI looks at the photometric multi-band data of the host galaxy, and it infers its star formation history and its expected dust distribution based on the laws of physics.
Okay.
And then it uses that latent information as a prior to constrain the state of the supernova. It uses the entire context of the galactic environment to separate the cosmic redshift from the local dust reddening.
Achieving precision comparable to spectroscopic measurements, but using only images.
Exactly.
It effectively learns to read the entire novel just by analyzing the cover art with an incredibly sophisticated physics-informed AI.
That's exactly what it's doing.
And the timing for this capability could not be more critical, because the field of astronomy is about to undergo a massive structural change. We are transitioning from an era of targeted observation to an era of industrial-scale sky surveys.
It is going to be a totally different paradigm. And the catalyst for this transition is the Vera C. Rubin Observatory.
Which is currently nearing completion on Cerro Pachón in Chile.
Yes. And the Rubin Observatory is fundamentally different from a targeted telescope like Hubble or the James Webb Space Telescope. It's designed to conduct the Legacy Survey of Space and Time, or LSST.
It's a survey telescope.
Right. It features a 3.2 gigapixel camera that is the largest digital camera ever constructed for astronomy, paired with an 8.4-meter primary mirror. Its mandate is to scan the entire visible southern sky every few nights, continuously for 10 years.
I mean, it is going to generate roughly 20 terabytes of data every single night. It's a photometric fire hose.
A fire hose is right.
Because the Rubin Observatory doesn't take spectra, right? It takes rapid-fire images across 6 specific optical bands, which are U, G, R, I, Z, and Y.
Yes, purely photometric. And the volume of transient events it will discover is staggering. Over its 10-year run, Rubin is projected to detect millions of type Ia supernovae.
Millions.
Millions. To put that in perspective, the entire history of modern cosmology up to this point has been built on a few thousand standard candles. We are about to scale up by 3 orders of magnitude.
That is incredible.
However, this creates what we call the 99% scenario.
Which ties back to the spectroscopic bottleneck we talked about earlier. We will have millions of new exploding stars captured in these beautiful multi-band photometric images, but there is simply not enough spectrographs on the entire planet to follow up on them.
Not even close.
Facilities like DSI or Foremost are powerful, but they can't point at millions of transient supernovae in real time.
No. At best, maybe 1% or 2% of the supernovae discovered by Rubin will receive spectroscopic follow-up. The vast, overwhelming majority, so 99% of our new standard candles, will be purely photometric data points.
Just blurry cover art.
Exactly. And without a framework capable of extracting precise cosmological parameters from photometry alone, 99% of the LSST supernova data would be largely unusable for the stringent demands of dark energy research.
That is a staggering realization. You build a billion-dollar observatory to map the universe, but without the software to interpret the blurry light, the hardware is severely bottlenecked.
Yes.
Konstantin Karchev, the lead author of the study from ICCUB and CISA Trieste, highlighted that CIGaRS was designed specifically for this. He called it a no-compromise end-to-end approach for this exact Rubin Observatory data.
And that term, no compromise, is vital.
Yeah.
It refers to avoiding the pitfalls of selection bias.
Selection bias.
Yes. When you rely solely on a spectroscopic sample, you are inherently biased toward observing the brightest, most easily accessible supernovae, because those are the only ones you can get a good spectrum for. This creates a severe Malmquist bias in your data. You are studying a skewed, unnaturally bright subpopulation, which ultimately warps your cosmological constraints.
But CIGaRS fixes that.
Because CIGaRS can handle the messy, purely photometric data directly, it can utilize the entire statistical weight of the Rubin survey. It analyzes the faint supernovae, the dusty supernovae, the ones in bizarre galaxies, incorporating all of them into the Bayesian hierarchy.
By utilizing the full breadth of the data without artificially filtering it down to the brightest 1%, the statistical power skyrockets.
It really does.
The authors of the study estimate that applying this AI-driven, physics-based modeling to photometric data could improve our cosmological constraints by up to a factor of 4 compared to traditional spectroscopy-reliant methods.
Think about that. A 400% improvement.
That's a 400% improvement in our understanding of the universe's expansion, just by changing how we process the light we capture. That means our ability to pin down the dark energy equation of state to understand if the acceleration of the universe will eventually lead to a big rip tearing space-time apart, or if it will stabilize, is drastically improved.
And the amazing thing is the data yield goes even further than the macroscopic fate of the universe.
What do you mean?
Well, because CIGaRS is jointly modeling the environment alongside the expansion of space, it inadvertently acts as a time machine for the stars themselves.
Oh, wow.
One of the longest-standing debates in stellar astrophysics is the progenitor problem for type Ia supernovae. We know it involves a white dwarf, but what is the companion star?
The one it's stealing matter from.
Right. Is it a single degenerate system where the white dwarf accretes plasma from a main sequence star or a red giant? Or is it a double degenerate system where two white dwarfs spiral inward and merge together?
And how does CIGaRS figure that out? It's looking at the delay time distribution, right? If you can figure out how long it takes a star system to form, evolve, and finally explode, you can figure out what kind of stars were involved.
Yes. But doing that requires knowing exactly when the host galaxy formed its stars.
And that is exactly what the CIGaRS latent modeling extracts from the photometric data.
Exactly. By analyzing the star formation history of millions of host galaxies and correlating that with the supernova rate, the framework maps out the delay time distribution with unprecedented resolution.
That's incredible.
If the explosions peak shortly after a burst of star formation, it heavily favors progenitor systems with massive, shorter-lived companion stars.
Right.
But if the explosions continue steadily billions of years after star formation ceases, it points toward double degenerate mergers.
Because those take an incredibly long time to shed orbital energy via gravitational waves before colliding.
Exactly. So by training an AI to understand the expansion of the universe, you automatically build a tool that reverse engineers the life cycles of the stars, fueling the measurement.
The interconnectedness of the physics demands an interconnected analysis.
It is the ultimate realization of the Bayesian philosophy. You cannot isolate a star from its galaxy, and you cannot isolate a galaxy from the expanding space it occupies. They are a single, cohesive physical system.
It completely reframes how we think about observational astronomy. I mean, we started this conversation by looking at a standard candle, a 100-watt bulb that we thought was simple and uniform.
And it turned out to be anything but.
Right. We found out that the bulb is tinted by the dust of its galaxy. Its wattage is altered by the age of its stellar neighbors, and the light itself is stretched by the dark energy accelerating the universe.
And the traditional linear methods of correcting those variables one by one have just reached their absolute limit. The error margins of our step-by-step math are now larger than the subtle cosmological signals we are actually trying to detect.
Which forced the development of CIGaRS, a unified Bayesian hierarchical model that maps the entire causal chain of the universe. And to solve the massive computational wall that such a complex model creates, we had to rely on simulation-based inference.
We had to bring in the AI.
We literally teach neural networks the fundamental laws of thermodynamics, gravity, and stellar evolution by forcing them to study millions of simulated synthetic universes. Also, they can instantly decode the blurry, multi-band images captured by next-generation telescopes like the Rubin Observatory.
It bridges the gap between theoretical physics and massive observational data sets. It allows us to embrace the 99% of data that would otherwise be discarded as too complex or too degenerate to analyze.
It is a profound triumph of software and statistical modeling acting as a multiplier for our physical hardware. But, it leaves me with a lingering thought.
Your thought?
We are entering an era where our most fundamental understanding of nature, the exact parameters of dark energy, the age and fate of the cosmos, is reliant on black box neural networks mapping the latent spaces of simulated realities.
It is a bit unsettling when you phrase it like that.
But if simulation-based inference can untangle the covariant physics of a supernova from purely photometric data, what happens when we apply this to the cosmic microwave background or gravitational wave astronomy?
The possibilities are endless.
Are we moving toward a fully differentiable digital twin of the entire observable universe, where every new telescope image just updates the master Bayesian prior of reality? What else might these simulated universes reveal that we haven't even thought to ask yet?
We've reached a point where the universe is simply too vast and complex to understand by looking through a lens with our own eyes. Our ultimate understanding of nature now fundamentally requires us to build artificial intelligences to interpret the light of dead stars for us.
It's a thrilling, slightly dizzying frontier. Keep looking up, keep questioning the models, and we'll catch you next time.